All right, so let's get started. Welcome back to the hybrid thematic program on modeling and theory in population biology. And this is a program of the Banff International Research Station. And over the next 5 months, we'll be bringing you a variety of online events in the area of modeling and theory in population biology. And today's event is staffed by Jake Pisaki from Banff International Research Station, and please send him a note in case of any technical problems. A couple of quick reminders on the slide of our mailing list, upcoming website, events for in the website for upcoming events. And I just wanted to draw everyone's attention to our next event, which will be in 2 weeks on the 30th. Where we'll have a career panel to discuss strategies and challenges involving job searches and careers in math, statistics, and physics departments. And coming up a bit later in our 5-month program, we'll have a similar panel focused on biology departments. About today's talk, within our 5-month program, we're planning to include a series of talks focused around the theme of applications of mathematical population biology, where mathematical models and theory have been important on societal problems. And particularly where members of our community have worked on these problems together with people outside the immediate scientific community. We heard a bit last week from Tanya Stadler about her work on COVID modeling and some of her efforts involving the government of Switzerland. Of course, epidemic models are only one of many areas where there's an intersection of population models and society. And that brings me to today's area, which is forensic population genetics. Of course, another really significant area where a background from mathematical models of populations has a major role to play in a significant societal problem. Today's speaker, Bruce Weir, has had a distinguished career in population genetics and statistics, but he's also been involved with the intersection of population genetics and forensic genetics really since the very beginning of forensic genetics as a field, first emerging in the 1980s and getting to be more commonly used and standardized during the 1990s. And Bruce has served on many different advisory panels for forensic genetics, both thinking about problems involving unidentified human remains, as well as forensic genetics in the criminal justice setting. And he's been recognized for this work, both within the population genetics and statistics communities, as well as within the forensic science community. And he's, for example, been elected as a fellow of the American Academy of Forensic Sciences. Today, Bruce is going to tell us about his work in forensic population genetics. Welcome, Bruce.
Thank you, Noah. Okay, so I need to share my screen. And there it goes, I think. No, excuse me. Wrong slide. How do I get out of this? Yep. Stop sharing. Share again. Share screen. And there it goes. And I need to view it.
It looks good. Yep.
No, does that look good? Okay. All right, so thank you, Noah, and apologies in advance for not having enough time to cover your own recent work. Very nice stuff on linking forensic and non-forensic databases. So this is meant to be a personal romp through the interesting world of law and science. And I hope I do better today than I did in Los Angeles 3 years ago. The LA Times was not particularly kind to me describing my talk on that occasion. So here's another report in the public domain. Maybe not dry as sand. President Clinton left some DNA on a dress, which got him into some trouble. And there were some numbers attached to the statement, and those numbers are certainly difficult to believe. And we're going to explore where numbers come from. So not as dry as sand, maybe, but I'm not sure if this particular statement was digestible either. So here's a recent case that I was involved in from Arizona. It was a homicide involving death by gunshot. The DNA profile from a swab taken from a trigger of a gun is a mixture. And one of the components of that mixture matched the DNA profile of a person of interest who turned out to be the defendant in a trial. And along with that statement came a numerical statement. The approximate incidence of this profile is 1 in a trillion Caucasians, and so forth. And where do those numbers come from, and do they even make any sense? They sort of beyond our normal way of thinking. So let's dive into that. This profile issue was a 9-locus microsatellite or short tandem repeat profile taken from the trigger and the person of interest. Each of the loci has 2 alleles. These numbers are just designations, basically the number of repeat units for the microsatellite, with occasional notational indications of some of the repeat units being incomplete. So that's the data. What do we know about that profile? So these are the data. This is a database used by the forensic agency in that case, where they had profiles, a few hundred profiles from different self-identified groups with somewhat unfortunate labels, I think would agree. I don't think I like any of these headings: Caucasian, African American, Southwest Hispanic, Navajo, and Apache. So I'm not sure what they mean. Anyway, here they are, sets of people, and amongst those people, the frequency of the alleles in that profile hovered around 10, 20%, something like that. And if you simply multiply together a column of 20 numbers of that order, you're going to get a score number. So that's not complicated. Problems with that. The first one being certainly the alleles can't be independent, as they're not. What about at a single locus? Let's make the problem easier. So this is an old problem. We call it the Hardy-Weinberg theory. And Eric Landon looked at this in one of the first cases to challenge DNA evidence, the Castro case in New York. And Eric said to justify applying our classic formulas, the Hispanic population in that case must be in Hardy-Weinberg equilibrium. And he conducted a test and said one finds spectacular deviations from Hardy-Weinberg. That's a very strong statement. It's somewhat surprising. It goes against what we typically find in samples of humans. We don't find many spectacular deviations. So this was interesting. Turned out, of course, that it may be the fact that in that particular typing system, heterozygotes are misclassified as homozygotes. Coming forward a few years, I was giving testimony in a homicide in Denver, and the prosecutor asked me about Hardy-Weinberg equilibrium. I did as best I could, and he said, well, what did you do about it? And the data you used, I said, well, I used Fisher's exact test for Hardy-Weinberg equilibrium. Immediate objection from the defense. They said that was hearsay, and if the prosecution wanted to talk about Fisher's test, they need to bring Mr. Fisher to the stand. It became very clear to me that I was wasting my time discussing Hardy-Weinberg equilibrium, or indeed anything in a courtroom. So I put my excursion into the law on hold for a few years. So still got large numbers, or very small numbers, and there's been several reports of the effects of increasing the number of loci in a profile. The FBI started using 13, and that's increased. Typically it's 20 now, but there are more, of course, many more microsatellite markers they could have used. And these people just give a little table showing the consequences by their methods of increasing the number of loci. And these are what they call the expected match probability. These are just numbers obtained by multiplying together 26 or 30 or 40 alleles, and they do indeed get smaller. The implication of these authors is that more is better. The more loci will give stronger evidence, making a coincidental match less likely. And these numbers are indeed getting quite beyond their usual experience. Their paper and that observation doesn't quite match with what Peter Donnelly reminded us a long time ago. After observing matches of some loci, it's relatively more likely that the individuals involved are related. They share DNA profiles, in which case matches observed at subsequent loci will be less surprising. That is, knowledge of matches of some loci will increase the chances at subsequent loci, in contrast to the independence assumption. So that's an obvious statement. We know it. We've done a lot of theoretical work bolstering that. Loci are not independent, even if they're in linkage equilibrium, and unlinked, that does not guarantee independence of genotype frequencies. We've published that many times to no avail, so we're resorting now to do numerical demonstrations. And here's a paper. We've shown this plot actually in other meetings, but this is a paper currently under review in the field. And on the x-axis, we've just simply reported the proportion of pairs of profiles that match, meaning all the alleles of the profile match. And this is just for the two loci. On the y-axis, we've taken the product of the single locus proportions, and they lie pretty much on the straight line, which is, of course, the reason why tests for linkage disequilibrium fail to find any. 3 locus matches still pretty close to the straight line, but then by the time we get to 4, and certainly by 5, we're seeing the observed and expected proportions beginning to depart. These points lie mainly below the line of equality, meaning that the observed matching proportions are bigger than we would predict by multiplying single locus proportions. So that's an uncomfortable observation, completely expected, completely ignored at the moment, I think, by the forensic community. But it's a fact we have to live with. So what can we do better? Can population genetics help us, as we would certainly hope? And some work going back a long way now, David Balding and Richard Nichols published a nice paper, and they borrowed the language appropriately of forensic science at that time, saying that if you're going to address a problem of evidence, you should have competing hypotheses, just as there are competing stories in a courtroom. One of them, that the person of interest is the source, for example, of the DNA in the crime scene. The defense hypothesis would be the opposite. The POI is not the source. And then there's some evidence, typically the profiles from the crime scene and from the person of interest. And it's standard practice to take a ratio of the two evidence probabilities, and providing the typing technology is good, and some other certainly weak assumptions, we can replace this likelihood ratio by the reciprocal of the conditional probability. What's the chance an unknown person who actually committed the crime under H2, given that we've seen that the person of interest has their profile? So we would call this the matching probability, and that's our term. Now, at the time of the Simpson case, 1994, US forensic agencies were using only the random men not excluded for mixtures. And they said they do that because it was easy to understand and the jury would be able to understand. And they as support, they cited a report from the National Research Council of the US National Academy of Sciences, saying that if a suspect pattern is found within a mixture, it's appropriate to assign a match frequency as the sum of the frequencies of all the genotypes that are contained within the mixture. So that sounds easy. It's completely worthless. It says nothing about those hypotheses, about the reason people are in court. It doesn't take into account the complete set of profiles. It certainly does not address mixtures. So I was asked to help the prosecution in the Simpson case by saying, in fact, there's an alternative to using the RMNE. And that was a novel thought at that time in the US. And there had to be a hearing, an admissibility hearing, to see if the prosecution was allowed to present something better. So one of the defense attorneys, William Thompson from UC Irvine, said a couple of months earlier, before the trial, in a chapter in a volume that I edited, as it turned out, he said, let's, beginning of his paper, he said, let's consider competing hypotheses for a DNA case. And for his paper, he said, let's consider our belief in how these hypotheses are affected by the evidence. So that's nice stuff. He must have forgotten he had written that because during the admissibility hearing, he objected to my testimony, saying, Dr. Weir has a tendency to slip into the language of likelihood ratios, and we certainly object to any such testimony. At that time, I was relying on work from my colleague Ian Everett, a United Kingdom forensic scientist, who had published a paper detailing exactly how to approach mixed DNA profiles using setting up likelihood ratios. And it was a nice 1991, 4 years before the trial. At the end of the hearing, the judge said he allowed the prosecution to present likelihood ratios. Looking back at the testimony of myself and the defense expert, Dr. Shields, I find the analysis offered by Dr. Weir is more accurate and closest to what the evidence truly presents. So under those restrictions, I'll allow testimony at trial. So the prosecution won that battle. Of course, they didn't win the war, so in a way, it was sort of a Pyrrhic victory. So moving forward to the trial, where I was on the stand to talk about likelihood ratios and mixtures. And one of the defense attorneys, Peter Neufeld, got a bit agitated. He said, the question, sir, I would like you to calculate the percentage of the population that cannot be excluded as contributing to this mixture, okay? That's a very different question than the question you answered to the jury, but it's a question I would like you to answer. Of course he would, because those numbers were quite different from the prosecution's numbers. They were helpful to the defense, and the defense was not about to present any numbers in that trial. So they wanted the prosecution to give their case. I said, I'm very uncomfortable doing that, because I don't think it's really probably a naughty statement and probably not very helpful. Anyway, there was some backwards and forwards, and in the end, I answered the question. Peter Neufeld was sanctioned by the judge for raising his voice. Random and non-excluded numbers were given in the trial, and in fact, they're still used today. Although, luckily, they are gradually being replaced, not by any effort from statisticians such as myself, but by increasing use of some software based on something called probabilistic genotyping, which in fact has likelihood ratios at its heart. So maybe the tide is turning. So back to the David Balding work. He having described likelihood ratios and so forth, went a bit further and assumed that allele frequencies in a population, if he assumed that they follow the beta distribution with parameters depending on the allele probability, and a parameter I'm writing is theta, and he called it FST at that time, then these match probabilities could be formulated. Just simple moment calculations for the beta distribution. Not complicated, but it has a very nice effect that the conditional probability of a genotype homozygote or heterozygote is bigger than the unconditional probability. So that the more you see, the more likely you are to see it in the future. And you can build up quite nice equations to handle complex situations. So these thetas, it's convenient to think about them as IBD probabilities for random pairs of alleles. Of course, behind the beta distribution, going back to civil rights work, there are some assumptions typically drift, mutation, equilibrium, and random mating. But a very nice result, and it turned out to be very useful. We've looked at the consequences of applying that in the multi-locus situation. We don't have sensible 20-locus versions of FST. So what is done in practice, which is helpful, is to use the Boolean-Nichols equations, the so-called theta correction for each locus, and then multiplying those single locus probabilities. So that's not correct, of course, and it's very conservative. So here on the bottom line, the x-axis, we've got observed proportions of matching at 5 loci, and on the x-axis, we've got the products of these theta-corrected single locus values, and it's the color changes, so does the value of theta. So certainly for theta 0, we've got a lot of points. In fact, the theta 0, forgetting this correction, the line of equality pretty much splits the observed and expected values equally. But as theta increases, the expected values become conservatively smaller than the observed proportions, and it would be certainly conservative, helpful to a defense to use a value of theta. So that's what's done. I don't think we've finished thinking about that, and certainly we could use help with other people thinking about the issue. I think if there's much debate going on at the moment, it's on Y chromosome data. Y chromosome is used on occasion as sort of an adjunct evidence, particularly for sexual assault. Interesting, in California, a Y profile match has to be shown before courts will allow familial search of a database for a relative of the person who left the DNA evidence. Anyway, so Y chromosome data is used on occasion. So here's a case from Alaska that I was giving some advice on. There was a DNA profile, and this sample was a mixture. The lab thought they could separate minor and minor contributors to the mixture, and they said the minor profile matched the profile from the person who was defendant in the case. And there was a number, as is required by courts. The DNA match is about 4,000 times more likely if the defendant or a relative, male relative, is the contributor than if a random man is. So that's obviously not a trillion, much weaker evidence, but certainly that statement as it stands is fine. There was another case, another sample of evidence in the same case with the same conclusion. This was it was a single locus item of evidence, and the same matching was found, the same profile, and also matching the profile of the defendant. So what are those two profiles, the two items of evidence? 22 Y chromosome microsatellites. Here's the person of interest. He matches where he can, as is almost always the case. If actual evidentiary profiles are not complete, so all kinds of things can go wrong, degradation, for example, and alleles. Some alleles were not typed. So that's there was indeed a pretty good match where possible. Interestingly enough, the prosecution had access to a native Alaskan database, and there was a profile in that database which almost matched the person of interest, except for one locus, so probably relatively recent male relative. So what's the big difference? What's the problem? Autosomal profiles have been interpreted as though the alleles were independent, which they're not. Y chromosome profiles assume the alleles are dependent, which they are not either. Mutation, we think, does act independently. So, and it's sort of odd because we've got no recombination. We find very little evidence for linkages to equilibrium between pairs of Y chromosomes. Anyway, so we have a match, and the prosecution is required to give a number. So that the simplest way, the naive way, is to say, well, how often does that type occur when we look for it? So let's take a sample of men, type them, and see how many of those men match the evidence. The answer is almost always 0. Because 20 locus Y chromosome match is not a very common event. So one simple way is just to say, well, I saw 0. How big could the frequency be in the population? And I get a 0. And for confidence limit, it's about 3 over the sample size. Nothing to do with genetics, of course, in this number. Nothing to do with the number of loci, really. So it's not satisfactory, but it's the preferred way currently for addressing Y data, ignoring population genetics. So the US used to maintain its own database, the US YSDR database. There's no longer funding for that. So the US depends on the European database, YHRD, a very large database maintained by some German scientists who do a very nice job of assuring quality of profiles that they accept into the database. And there's a little description you can find about it in Wikipedia. It has 350,000 profiles and 100,000 of the most commonly used commercial typing kits. They claim to be open access. Of course, they're not. You can certainly go to their website and type in a profile and get an answer, but you can't get the data. And that's a result of European privacy laws. So I typed in the profile in that Alaska case. Here are the 22 loci, here are the alleles, and using 100,000 or 93,000 profiles in the database, there was no matches. And they gave a confidence limit. So if they don't occur in the whole database, they certainly won't occur in a subset of the database, which includes US profiles, and they certainly don't occur in any subset of the US data, which have these unfortunate post-ethnic labels on them. So the profile doesn't exist in the data set. So what can we do? Going back to the Baldwin-Nichols idea of bringing in an IBD probability, we know what those values should look like roughly for random mating populations and the drift in mutation. For stepwise mutation, Oger and Kimura gave a formula a long time ago. It has the same flavors as our typical 1 over 1 plus 4n u, but ends the number, in this case, of Y chromosomes and use the haplotype mutation rate. The point is that as we get more loci in the profile, there's more opportunity for mutation, so the mutation rate goes up, so theta will go down. So the probability of a match will go down with more loci, as we would expect. Formalizing that, this is a very standard equation. What's the chance of 2 profiles being the same type? They depend on the probability pi of one of them being of that type, and then this parameter, which we can think about as being an IBD probability, or it could be a correlation, going back to Silverbright's work. And if we just divide by pi, we get the match probability, which is theta plus some other term. This is, of course, bigger than the chance of seeing it a second time is bigger than the chance of seeing it the first time. But maybe more interestingly, this probability, this match is bigger than theta. So maybe theta gives in itself, even if pi gets very, very small, theta is giving us some guidance on what's the chance of a coincidental match. So there's 2 problems with that equation. It's 2 parameters that we know neither of them. So we don't know the probability of a profile being of a type, and these are our profile use the probabilities. And in particular, we don't have a good way of estimating pi squared. We can estimate pi by taking a sample, but to estimate pi squared, we need information about the variance. We don't know pi, and we don't know theta. We can get some guidance. So we've been resting on some of the recent work with Jerome Goudet, where we have revisited the problem of estimating FST, and we work with what we've called allele sharing or allele matching, sort of borrowing from the forensic needs. What's the chance that 2 profiles have the same type, or they depend on the theta value for the population containing those profiles, and they depend on this unknown sum of squared probabilities. That's within a population, and going back to civil rights ideas in the 1920s, you can't really address probabilities in isolation, and Elizabeth Thompson's made that very clear. We need some reference point, and the reference point we've adopted is the sharing or the matching between pairs of populations. So there's a theta for each population, and there's an analogous quantity for pairs of populations. So instead of estimating the target parameter theta, which we don't believe is estimable in general, we estimate this compound parameter, which is the matching within versus the matching between. And it's interesting, this is a very simple idea. It seems to work pretty well. We rely on some nice work by John Story showing that this ratio converges almost surely to the parameter value as the number of loci increases. So the fact that it's a ratio is not a problem. And it's interesting, if we had equal sample sizes, this is just the same equation as the Weir and Cochrane estimated some 40 years ago. So we've estimated theta, and in the process of getting that published, we don't have the YHID data, which is by far the biggest data set. There are several published sets of around 20,000 profiles, not really enough to do much with. What YHID did do, luckily, is give citations to their data sources where they were published. So we've looked at the data, the publications, and harvested the profiles and constructed our own database. And that's about 70,000 profiles. So still not enormous, but certainly we had 50,000 or so useful 22 locus profiles. 22 was the number in one of the big, mainly used commercial typing kits. And these are from several different populations falling into 6 broad ancestral groups. So we have done that, and partly in plea to a statement from SWGDAM, which is the FBI's working group on DNA analysis methods. So we find estimates which are broadly consistent with the SWGDAM guidelines in 2014. The current guidelines do not show estimates because the SWGDAM considers the issue too unsettled to publish data. Anyway, here are the estimates we've found, all times 10 to the power of 5, and with these broad continental grouping labels using 1,000 genomes notation, and they get the estimates get smaller as we get more loci, but the rate of decrease changes. And just plotting that, the matching proportion on a log scale goes down as the number of loci increases for a while, and then it increases, looks like it's increasing quite steadily. And then we run out of data because even with 50,000 or so and it didn't make much difference whether we had African, European, or Asian samples. We get this pattern. But we ran out of data. We don't have many matches, more than 17 or so loci. We've done some simulations up to 50 loci, which what we thought was a sensible model, and we get the same. We get an initial dip in the log matching, and then a steady increase, but at a decreasing rate until we ran out of data. So that's about where we're up with the Y chromosome data. The issue is forced on us in a way by needing to demonstrate that we're capturing the strength of a multi-locus profile. And we're in the situation where legally prosecutors are required to attach numerical strength. It'd be a lot easier if they simply say, here it is, here's the match, and we think this is the person, which is what handwriting experts are allowed to do. That's not satisfactory either, so probably it's good to try and attach numbers where possible. There are other ways of thinking about allelic association is the novel concept of entropy. Just remind you that entropy is the sum. If you've got a category with types U, the entropy is the sum of the type proportions times their log. So if there's only one type in the sample, one of the p's is 1 with a log of 0, so there's 0 entropy. As they get more and more types and they're equally frequent in the sample, then the entropy reaches its maximum value of 1 over the number of types. So this is a useful concept, and particularly because it has this simple additivity problem issue with property when there's independence. So here's the entropy for a 2 system, maybe two locus profiles. All the types for the alleles at the 2 loci, the log of their sample proportion, and if they were independent, if the sample proportions were products of the allele proportions, so we just got the sum of the logs, and the joint entropy is the sum of the 2 single locus entropy. So that's the issue, the fact that we can exploit. So entropy is additive when there's independence, and that gives rise to the concept of conditional entropy. The entropy of B given A is the joint entropy minus the entropy. So we've looked at data and started with a series of Y chromosomes and started out choosing the locus which gave the highest single locus entropy, and then chose the locus with the highest conditional entropy and proceeded. So here, these are actual data, 20 or so Y chromosome markers, the single locus entropes, and the conditional ones by construction, the way we ordered them, go down steadily. But after a while, the conditional entropy decreases, and after a while, the overall entropy, the overall measure of diversity, is not changing substantially. So it'll continue to change, of course, if we have more decimal places. But it looks like, as a practical matter, in this case, it doesn't make much sense to get more than a dozen or so loci, because you're not going to change the sort of the overall measure of information. So just to wrap it up, what have I said in this little personal tour? Population genetics can be useful, can guide the interpretation of DNA profiles. The strength of the evidence depends on the probability of the evidence and the alternative hypotheses. And this statement is a paraphrase of what Ian Evatt called the first principle of evidence interpretation. And these probabilities are shaped by evolutionary forces about which we know something, or we can make statements. And they're certainly simple to think about and easy to demonstrate that probabilities decrease, but at a decreasing rate as we get more loci. So that's simple, but we're scientists, and we need to be careful, as I found. So the very goals of science and law are different. Science searches for the truth and seeks to increase knowledge by formulating and testing theories. And I would say we're looking for generalities and patterns in data. Law seeks justice by resolving individual conflicts, although the search often coincides with the truth. Rules of decisions that are not tailored to individual cases, such as those that turn off statistical reasoning, are often viewed as suspect, as indeed they are. So that's the caution, the lesson that I have learned, which makes life very interesting. So thank you all for paying attention, and I look forward to further discussion.
Okay, thank you so much, Bruce. So I guess for anyone who has a question, you can raise your hand, and then call on you and can unmute and speak in this forum. And while people are thinking of questions, maybe can I ask you a little bit, Bruce, about, you mentioned a California law that involved a Y chromosome profile being needed in order to pursue familial searching. I'm curious about that, and about scenario where the relative might not be on the male line and
Yeah,
might
yeah, no, good question. So the use of familial searching is not widespread. It's where it has been used, it's been found to be useful. So this is when an evidence profile is obtained and searched against a database. So the CODIS database is 20 million profiles, and it's quite large. But even then, it doesn't have everybody. So it's very often the case that the evidence profile does not have a match in the database. But there may be profiles in the database which match at most of the loci. Maybe a few alleles differ, strongly suggesting that the database profile was from a relative of the evidence donor. So one way of just simply doing it is to do one of these so-called familial searches, looking for profiles like that. The problem with that in practice is that it can turn up a large number of close matches, and that's, practical matter. It's a lot of work for investigators. More importantly, it brings into the attention of the authorities people who are completely unrelated to the crime and the person. So there needs to be. It was thought, as different states have wrestled with this, a lot of states just simply prohibit the procedure. California allows familial searching, but only for sexual assault cases where a wide profile match has already been found. So they know, and not found in the database, in their database. So they know that this. I've got this right. They've got evidence that I'm going to get into trouble now. They've got evidence that the profile is not in the database. I forget. I'm missing. Maybe that's your question. I'm forgetting the logic. But then the prosecutor has to show that before they're allowed to proceed for an autosomal familial search. Can you help me there? I'm forgetting a bit.
Yeah, I mean that sounds
and maybe you could regard it as an attempt to reduce the burden of investigation, but it does require a wide profile.
Yeah, I guess there's sort of been the different approaches that different states have taken to the familial search, where
yes,
in some it's not allowed, in some it is allowed, and then California kind of taking this somewhat intermediate position.
That's right. Yeah, that's right.
Great. So John Wakely has a question.
Hi, Bruce. Thanks for an interesting talk. I really take to heart your point at the end about the the different goals of the courtroom versus science, and I wonder if you could say a little bit about that. It strikes me that for me there's something a little bit uncomfortable about putting a lot of fancy statistics with numbers to what ends up being a binary decision in a forum that is really unlike what we do in science. And I'm not sure what to do about that. And if we're a really good statistician, for example, we might end up wanting to calculate a number in the end and then, flipping a coin and letting the person go with some small probability or something like that. And so a lot of different ways one could make these decisions. And I don't know that we do it in the best way overall.
Yeah, no, I think I share your concerns. So, and I didn't go into all the discussion around likelihood ratios. It's only a likelihood ratio. It's only the ratio of probabilities of evidence. It is not what the court wants. The court wants to know if this person committed the crime or not. And, rules of evidence and rules of procedure suggest they should adopt a decision that gives the most likely being the correct one. So decisions are made by judges or juries, and that's their business. We are not allowed and shouldn't tell them how to vote on conviction. So this is an attempt to guide their decision making. The decision is theirs. It doesn't matter what the likelihood ratio is. They can decide to convict or acquit depending on their individual beliefs, and that's our system, and I think it's a good one. So that we're not telling the court how to behave. We're providing them with the evidence. And it's not helpful to say there's a matching profile, and this is a very rare event. Of course it's rare. 20 locus profiles are not common. So don't tell me it's rare. That doesn't help me at all. But tell me, well, I see a match and the chance of seeing it again, that's rare. And then this is what I try and explain what rare is. And if I have to do it, I talk about lotteries and having the best one I got heard was a slot machine with 20 wheels. And if you pull the lever and get 20 wheels showing the right fruit, that's a rare event. And you get the payoff. So trying to put some sense, and I really don't like these large numbers. I think they are misleading. I don't know what they mean. So the locus assumption of independence does bother me. One way around that is to adopt Jim Crow's fable. Why don't you just say, what's the chance that a brother or a sister of the defendant will have the same time, or of the perpetrator will have the same time? So try and give some context and don't go beyond that. I used to advocate for not giving numbers at all. I think I've backed away from that. So in the UK, they say once the number reaches this threshold, which could be 10 million, the FBI tried to do that, and their calculations were a bit dodgy. They tried that, and the prosecutors did not like it at all. They didn't want to get up to falling off a cliff effect. They don't want to say, well, up to this point, I've got to give a number. Beyond that, I can say it's the person. And that's why that Clinton quote had this meaningless phrase, a reasonable degree of scientific certainty. That doesn't help.
Well, this is part of the problem, is that there's this language about reasonable doubt, which it seems like we should have something to say about because we're dealing with chances, but we really shouldn't, in a way.
Well, we know a lot about reasonable doubt. Surveys have shown that it's completely useless. The reasonable doubt means different things to different people. So there is no numerical standard.
Yeah.
I can't disagree with anything you're saying.
Thanks.
But I've been wrestling with it.
Great. Thanks. Yeah, and so I should also mention, for anybody who has a question and would rather just write it in the chat, you can do that as well. And just this discussion is very much in the spirit of what we're thinking for this line of talks on applications and trying to square different cultures within our field as well as outside of it. So thank you for all those comments.
No, maybe I can give a little plug.
Yeah.
A little plug for this probabilistic genotyping measure. So it used to be that the forensic agency would do a typing and say these alleles match or they don't match, and do not match was an exclusion, and that was the end of the story. Probabilistic genotyping, and behind that, of course, was some decisions made by the analyst about whether there was enough DNA in the sample to give a reliable signal. So there were hidden thresholds beyond which, above which they would could declare a match or not, or simply ignore that locus, which is not good either. So probabilistic genotyping says let's model the typing system and admit the fact that we see something in the typing technology, and most typing is an electropherogram. It's a trace. It's a series of peak heights representing the amount of DNA in the sample. Let's model the process leading to those traces and not declare a match or an exclusion at all, but to attach probabilities to what we see. So it's model dependent, but they end up with a probability statement, which they can then use for likelihood ratios. But there is no absolute statement made anymore. So I think that's quite nice. So there's no such thing as an exclusion. Anybody theoretically could match any profile if enough things happened during the typing, enough problems with amplification and misinterpretation and so forth, or stutter, or mutations. Anybody could match any profile, but you're going to attach probabilities to what you see in the data. So I think that's a big advance. It's very nice work, very hard to explain to a jury. So in a way, things have gotten worse. Now it's very much a black box. But I think that's a step in the right direction.
Great, thanks. So there's a comment in the chat from Jane McDonald that there's a book called Math on Trial: How Numbers Get Used and Abused in the Courtroom. And maybe that leads me to another question, which is, I mean, you mentioned handwriting, as kind of another area of forensic evidence with different standards. And, I wonder if you have kind of any remarks on, forensic genetic evidence is supposed to be the gold standard for scientific evidence presented in courtrooms, and kind of the burden that places on the field, and kind of the challenges that come from forensic genetics, having this somewhat elevated status. Kind of curious about your thoughts.
That's nice. So of course we're lucky with these DNA profiles that they are genetic, and we know quite a bit about genetics, and there is a random process underlying them. Handwriting, I'll take as an example, maybe not quite as clear, although there have been experiments done to see how often handwriting from different people matches. It's interesting that Goldman's book on fingerprints, the conventional fingerprint, in 1892, reported his experiments. So he did a lot of experiments. He made fingerprints and cut them out and shuffled them and did all kinds of credibility studies and so forth. So he attached numbers to fingerprints. They were mind-bogglingly small as the DNA profiles are. But he did that, and that was a brave attempt. There's been some discussion about doing that for DNA fingerprints in the US. Probably, the conventional fingerprints probably won't proceed. But like all type, there's other things that can go wrong apart from the numbers. I mean, certainly we've seen instances where the wrong person's been declared to match. So if you ask a fingerprinting expert on what he bases his judgment, he says, well, I've been trained, and that means I went to a course and I did a test at the end. I was given 100 profiles and I had to match them, and I passed. End of story. I see Reginald had a question.
Yes, yeah, Reggie. Yeah, go ahead, Reggie.
All right, can you see me now?
Yeah.
Okay, hi, Dr. Weir. I have a quick question. From the slide you showed in the beginning about the supposed 1 in a trillion chance and then the conditional entropy on the later slide, I was wondering if the people out there in the field generally realize that once you get beyond a certain number of microsatellite loci, especially since they have so many alleles, that you're getting more possible matches than people have ever existed or ever will exist, probably. And so, like, I could throw out 50 loci with maybe 10 alleles each locus and say, oh, there's only 1 in quintillion chance that this is wrong. But does that really mean anything, since the set of actual people is a lot smaller that you're comparing against?
Yeah, I try and counter that by saying these are probabilities, they're not proportions. So the size of the Earth's population, current or previous, has, I say, nothing to do with it. So we're not estimating the proportion of actual people with the profile, and that's and it's very hard to. I think it's not an easy concept, and I don't know how to make that distinction. I do talk about tossing a coin and giving it, say that there's a chance of 1 in 2 that I'll see a head. Even if I don't toss the coin 2 times, the chance is still 1 in 2. The chance of 1 in a trillion has nothing to do with the size of the population. It's a probability. And that's the issue, of course. What does that mean? It's not a proportion. But I mean, I'm agreeing with you, but I'm just saying I'm not worried about the size of the population.
Oh yeah, I'm sure you're. I just when people throw numbers out there, sometimes I don't know if they think about how they're stating things. And yeah, it is I understand the probability aspect of it.
Yeah.
Obviously,
I know you do. So, but that is, I mean, that's one problem we have. to
Yeah.
try and explain what it is we're doing.
Yeah, and I guess
you.
you were alluding to that sort of right at the end there, Bruce, about the probabilistic genotyping, and I guess as the techniques get more sophisticated, and whether kind of how the field thinks about the say the statistical justification of the method on one hand versus the challenge of communicating that method in a court setting on the other hand, and maybe experiencing this also now with genotype imputation, being another method that's kind of in that same space as probabilistic genotyping. Same sort of challenge.
Yes, yeah, and it's been adopted more widely. The only reason it's been adopted is that they can get a result from problematic cases. They can get a result where conventional interpretation methods were failing. So it's sort of not a good justification. But yeah.
Yeah, thanks.
So maybe just one more question about the you mentioned the 70,000 Y chromosome profiles, and and how kind of challenging it was to assemble all of those from a very large of studies, and
it's huge.
And so maybe just curious about your thoughts on databases of forensic profiles, and what's missing, and what's needed, and kind of the challenge of a setting where there's protections of privacy on profiles that are used in actual cases, but some need to have profiles in order to look at the calculations and do those better.
Yeah, well, I would really love to see publicly accessible databases. This 20 million profiles in the CODA set is a target completely protected them, but neither you nor I are ever going to be able to see those data, and maybe with good reason. It's very hard to, even 70,000, 100,000, or a million profiles is never going to give us reliable estimates of 1 in a trillion anyway, so maybe it's hopeless. It's interesting though. So we read 200 or 300 papers and downloaded their spreadsheets, and about half of them were clearly wrong. I mean, simple things that we could test, like making sure the proportions add up to 100%, or making sure that the allele designations were recognized labels, or any number of things. And we wrote the authors, I say we, it's John Buckleton's work, wrote the authors, and some of the time they responded saying, oh yeah, thanks for pointing that out. So the errors are, the published data are full of errors that we know about. Then we found instances of high degrees of matching, lots of profiles. In this one particular study, the authors said they took care to sample unrelated men. We found multiple instances of the same profile, strongly suggesting common paternal lineage. And you certainly want some relatives, but you don't want the sample to be enriched for relatives. So it's very difficult in practice. Does the big genetic studies help us? Does the UK biobank data help us? Maybe. We can certainly translate from SNP profiles to SDR profiles, as you know. We could construct databases that way. Would that help, or would people want us to use the data that way? I'm not sure. So we're in a bind. We if I'm helping the community, try to help both defense and prosecution. If we are to help, we need to help them meet their goals of giving numbers, or argue against doing that. So we do the best we can, and that we are helped by having more data. I think if we can, we've already demonstrated, I think, convincingly that 5 locus matches are not the product of 5 single locus matches, although if we put in these population structure corrections, we overcorrect, so we're not doing harm. So, but that's a data demonstration, which I think is useful. Will there be more data? Probably not, I would think. Reality.
Okay. Well, thanks so much. So we've reached the end of the hour here. Right on time. I'd like to remind everyone that we'll see you again in 2 weeks for a career panel on academic jobs in math, statistics, and physics departments. And thank you again to Bruce for really a terrific tour through your work on forensic genetics and the personal perspective on the field. Look forward to seeing everyone again in 2 weeks.
Thank you.